Hello, welcome to physics lesson 4.01, force introduced. This is the first lesson of our next uh, packet, chapter, whatever you want to call it. And it's a quick one. It's also almost all concepts. So what we do with forces is they're important enough that we split them into two chapters. And we take about, a week and a half to go over the concepts of force and Newton's law and free body diagrams. And then we'll put the mathematical portion of it in chapter 5. That's why you'll notice if you look at the assignments for chapter 4, there really aren't that many. You do have the physics packet that I gave to you in class, and you'll do some quick hitting problems from that. But they don't take more than like 10 minutes or so, so they're very quick. To start with, let's define a force. A force is anything that causes an object with mass to change velocity. Anything that causes an object with mass to change velocity. And knowing the definition of velocity, you understand that means acceleration. Or direction. Or change direction. Anything that causes an object with mass to change velocity or change direction. Well, aren't those always together? I mean, if you slow down, if your acceleration, if you decelerate, you're, in a sense, isn't your directional values changing? Well, what if you were going in a circle at a constant velocity? So in that case, your velocity isn't changing, but your direction is. And we'll get to that later in the year. So some background. We have the unit is called a Newton. And that's actually shortening up, it's a derived unit. It equals a kilogram times a meter over a second squared. And the symbol that we use is a capital F. And there'll almost always be a value here. So like if we're talking about the force of gravity, that'll be F sub G. If we're talking about, well, I don't want to get too far down the road, but we'll often have a subscript here. There are 4 categories of forces. So there are 4 categories. We have the strong nuclear force, number 1. This is the force that you saw, and when you watch a video clip of an atomic bomb being detonated, that's strong nuclear force. That's the work that's being done as a result of releasing that energy that's stored in the nucleus. You have another nuclear force, though. It's called the weak nuclear force. There's some minor radioactive decay that we see with the weak nuclear force. Number 3 is gravity. And number 4 is electromagnetism. You might be saying, all right, hold on. I know if I push on a box, I'm exerting a force on that box. And you don't have on your list anywhere push or pull. So what's up with that? Well, it turns out that electromagnetism has a whole subset called contact forces. We have electric fields, we have magnetic fields. So I'm going to do this. We have electric field force, We have magnetic field force. And then we have a subgroup called contact forces. Contact forces. And that also brings up another point. So we talk about forces in terms of field forces, and we know that gravity, this is a field force. A field force does not have to be in proximity to act. A field force is exerted over distance. So even a satellite that's orbiting the Earth feels the force of gravity, even though it's not in contact with gravity. So we have to handle these in their own category. We don't do electric field force or magnetic field force in this physics. That gets handled in physics 2. So what's up with this contact force? How could it be electromagnetic if it's in contact? When I lay my hand on my paper, my hand's now in contact with, and I'm going to say the desk because the desk is right underneath it. So how is this electromagnetic? Well, the atoms in my hand are mostly empty space, and the atoms in the desk are mostly empty space. So what prevents my hand from slipping right through the desk? Really, there is no reason why the atoms of my hand and the atoms of the desk can't occupy the same place. Well, it turns out, remember what's on the outside? Most of you, I think all of you took chemistry. The outside of an atom are electrons. So I have a field of electrons on the desk, and I have a field of electrons on the palm of my hand. And what happens if you put electrons next to electrons? Like charges repel. So what we're seeing here is actually repulsion between the desk electrons and my hand electrons. So contact forces, even though we think of them as touching, are in a sense electron-electron repulsion. But it does make up a subset. And we're going to spend probably 80% of our time working on contact forces. So let's talk about the different contact forces. There are 6. There are 6. And the criteria is in our mind, so actually at an atomic level, my hand is never in true contact with the desk because the electrons are repulsing. But we think of a contact force as it exerts through contact. You have to be touching. Gravity, you don't have to touch. Electric field, magnetic field, you don't have to touch. We will actually do a little bit of the strength of electric fields. We do just a teeny bit with this. We don't handle this at all, but we do quite a bit with gravity. But you'll have to remember, field forces, contact forces, we handle them a little bit differently. All right, so how many contact forces can you think of? Take a second, pause the video if you need to. All right away, most people are able to think of applied. This is what we think of as a push or pull. That's an applied force. Sometimes people will get friction. You can experience this. You take your hands, rub them together, and you generate heat. So friction is a really big contact force. And sometimes that's all we get. Every so often, people will get tension. This is a force through a rope or a string or a wire. Sometimes people will get spring force through a spring. So if I have, oh gosh, one of those the little poppers that you push down and you load the spring and then you wait, and after a while it pops up, that's spring force. The one, two of them that people usually don't think of, this one you've probably never heard of, the normal force. So when I push down on the table or the desk is pushing up on my hand. There's a force exerted on my hand by the table at a 90-degree plane, and that's the normal force. So this is the force exerted by a surface at 90 degrees. So for example, if my surface is here and I have an object, we're going to say that the normal force, and the abbreviation for that's going to be F sub n. So if this is my surface, the normal force is exerted by the surface 90 degrees. But what if I have an object against a wall? Well, now my normal force goes this way. That's not exactly, sorry, that's a little off. But it's always 90 degrees to the surface. If I'm on an incline, my normal force is going to go here, 90 degrees to the surface. So you have to remember that starting off, we're always going to have a normal force that looks like this, but we can later on have a normal force that looks like that or like that. The last one is air resistance. And this is the one we pretty much ignore. Whoops. R resistance. This is the effect of molecules, air molecules acting against an object as it moves. And for the most part, we always just say, pretend like this doesn't exist or ignore this. So what you have for your first kind of quick hitting activity in the packet that I gave you is you have different scenarios, and you have to determine what forces are at work. So let me give you a sample problem before we go. So if I throw a ball, and it is traveling through the air, what forces are at work? If I throw a ball and it is traveling through the air, what forces are at work on the ball? So here's my ball. One of the things you'll see that I'm going to do fairly frequently is when we get into drawing our diagrams, we get a little more complex, I use a green vector arrow to represent motion. So this is my motion vector, and it just tells me, you know, this is what's happening with the motion. All right, so take a second and think about it. Pause the video if you need to. What forces are at work? Okay, the answer is just one: gravity. maybe you said, wait, there's an applied force. Remember, applied is a contact force. When the ball is sailing through the air, is it in contact with my hand? No. So that means that this is not possible. The only time that force is applied is right at the beginning when it's in contact with my hand. When I'm flowing or flying through the air, actually there's two. There's gravity and there's air resistance, but we always ignore this. So, but if you had said air resistance, that would have been correct too. But not applied. All right, so that is our introduction on the categories of forces and the definition of force. Thanks for watching and have a good day.